Okay, so today we're going to be going over longhand electron configurations for the elements on our periodic table, and we're going to also go over exceptions. So before we go over some configurations, I want to go over what you're writing in your configuration, the different parts, and then we're going to look at our periodic table and our diagonal rule to write our electron configurations. So before we start doing this, you might want to pause this screencast, get out your periodic table, and also get out your diagonal rule because you'll be using both of those. So the number in front is the energy level. And if you remember from what we talked about before, there's 7 energy levels on your periodic table. So this number can be anywhere from 1 to 7. The letter is your sub-level. And if you remember from last class, we have S, P, D, and F. So that's 4 possible letters there. The number that's a superscript to the right is the number of electrons that are present in that particular sublevel. So for the case of P, this can be any number from 1 to 6. It cannot be over 6. So I want to go to the next slide, and we're going to practice with some of the elements that are in this presentation. So the next slide, we have hydrogen. If we look at our periodic table, hydrogen has an atomic number of 1. And if we look at our diagonal rule, the hydrogen, we always start with 1s. So let's go back, and we would write 1s1. If we look at lithium, lithium has an atomic number of 3. So we would write 1s2. 2s1. And if you look, the superscripts add up to 3. And if you also look at our diagonal rule, we're starting with 1s. When that's filled, we go to the next one, which is 2s. So let's do another one. We have nitrogen. Nitrogen has an atomic number of 7. So we have 1s2, 2s2. This adds up to 4. We have 3 more. We look at our diagonal rule. We see that after 2s is 2p. So let's go back. And then we have 2p, and that would be 3. If you look at 2 plus 2 is 4, plus 3 is 7. We look at neon. This has an atomic number of 10. We have 1s2, 2s2, 2p6. We have 2 plus 2 is 4, plus 6 is 10. That we're done. Potassium, let's look at our periodic table. Potassium has an atomic number of 19. So let's go back to our slide. We have 19, 1s2, 2s2, 2p6, that's 10. So let's look at our diagonal rule. After 2p is 3s. So let's go back. 3s2. After 3s2 is 3p6. We have 18. So we just have one more. If we go to our diagonal rule, after 3p is 4s. So let's do that. And that would be 4s1. Okay, so this is how you write an electron configuration. And if you do not have enough electrons, you don't have to fill a particular sublevel. Your superscripts should add up to your atomic number. Once those add up, you're done. So I want to go over a few exceptions on your periodic table. So what we see is some actual electron configurations are different from what we expect based on the off-ball principle. So remember, the off-ball principle says that we fill the lowest energy sublevels before we help fill the higher energy sublevels. The reason why it's different is because half-filled sublevels are not as stable as filled sublevels. but they're more stable than other electron configurations. So what we see here is, for example, for copper, what we would expect is that it would be end in 4s2, 3d9. What actually happens, it ends in 4s1, 3d10. This is a filled D sublevel. This D sublevel is filled. This is very stable. So it'll shift an electron from the S to the D to make that very stable configuration. So on your periodic table, I want you to star group 11. We see this with copper, silver, and gold. So if I ever gave you roentgenium, we'd also see it with that. So let's go back. We also see this with group 6. With group 6, for example, with chromium, we would expect it would end in 4s2, 3d4. What actually happens, it ends in 4s1, 3d5. This is very stable. So half-filled or filled D sublevels are very stable, and the element will make adjustments to make that very stable configuration. So on your periodic table, I want you to also label group 6. So we see this with chromium, molybdenum, and tungsten. If I ever gave you seaborgium, we would see it with that also. So what I want you to do now is stop this screencast and do some of the longhand configuration problems on the worksheet that's on Google Classroom.